Alright gang, here we go. This is Chem 2, Unit 2, Chapter 6. We're going to be talking about orbitals today. So last video we ended talking about the Bohr model, and we ended talking about limitations of the Bohr model and how it only works for hydrogen. Alright, now we're going to talk about orbitals and kind of how scientists took the Bohr model and expanded upon it in order to make predictions for all the other elements. Alright, so here's the two important things that we took away from the Bohr model. Number one, that electrons can only exist in certain discrete energy levels, okay, and these are defined by their quantum numbers, and so we'll talk about the quantum numbers here in a second. Okay, so remember Bohr said that he had these energy levels, N1, N2, N3, etc., that electrons could only exist on, and then we took this, scientists took this idea and expanded upon it, and saying that, that electrons can only exist at these discrete levels, and then they came up with a series of numbers that allow us to determine what those values are. Okay, and then number two was that in order to move from one energy level to the next, we have to incorporate energy in some way. If it goes up, we have to absorb energy. If we go down, we have to release energy. All right. So along came de Broglie, right? Louis de Broglie. Okay, he theorized that if light can have material properties, right? So that was bizarre, right? And for a long time, people only assumed light were waves, right? Because you can't really touch light. I've got light coming down from my ceiling right now. I can't touch it, right? So they thought light has to be a wave. I can't touch the waves, right? But then we've shown that there were certain aspects of light that showed that it had to have material-like properties or particle-like properties. All right. So he theorized. He said, well, if light can have material-like properties, then maybe all matter exhibits some sort of light properties. And through complex theories and years of work, he developed this relationship between the mass and wavelength and velocity. So if you know the mass and the velocity of something, you can determine the wavelength that it's moving on. And look at this, it's also using Planck's constant. As you move through science, you'll notice that this number, Planck's constant, plays a vital role throughout all of quantum mechanics. It's kind of bizarre, like this number was discovered so early in the development of quantum mechanics, but it's kind of set like a really important value. It's pretty cool. But anyway, so he determined this idea that all matter kind of has a wavelength. So even though I'm sitting here not moving in my chair, but I'm moving in relation to into space, right? I have some sort of wave-like property, right? Now it just so happens that my mass and my velocity are so low, or so big that my wavelength is really, really tiny. So it's like it doesn't even register. Okay, so along with that idea that matter can have wave properties, and so as you get smaller and smaller, you have more and more wave-like properties and more and less material-like properties. Heisenberg came along and said, well, he came up with this idea of the uncertainty principle, okay, that when you have something that's extremely small, that the more you know about its momentum, the less you can possibly know about where it is. Okay, and then vice versa. The more you know about where that particle is, the less you can possibly know about its momentum. So that's the idea of the uncertainty principle, is that if you have a particle and you know exactly where it's going to go and how fast it's going to go, you can't know where it is. Right at that moment, you can know what direction its momentum has and how fast it's going to go, but you don't know where it is, and then vice versa. Okay. And down there is the mathematical relationship. Don't worry about that for now. All right. So along with those ideas there, along came Schrödinger. Okay, and he developed these things called the wave equations. It's a mathematical treatment. It's just a fancy way of saying he came up with a bunch of equations to mess with this, and these are quite complicated equations. Okay, but it was this mathematical treatment, okay, that you could explain and incorporate both the energy or the wave-like properties and the mass and the matter-like properties that this particular element has, or this particular whatever it is you're talking about has. Okay, and so him developing these things was this breakthrough that we'd been looking for, and so it was quantum mechanics. All right, so this is where it came up with. And so in essence, what you need to know about this is he came up with these things called wave equations, and this is the symbol he used. Okay, it's kind of like a trident. All right, so these wave equations allowed us to predict where electrons would be. Now, remember, based on the uncertainty principle, we could not predict where it would be going, okay? So anyway, when you're looking at this, this is a three-dimensional graph, okay? So our x is coming in and out of the page at you. So that's kind of what that means. And the y is horizontal. And the z-axis is vertical, okay? And so these blue dots represent likelihoods of positions for the electron in this area. Okay, so this is looks like a 2D circle, but really remember, because that x is coming in and out of the page, is actually making a sphere. All right, so areas where there's lots and lots and lots of blue dots is a high likelihood of finding the electron there, and places where there's not a lot of blue dots, there's a low likelihood of finding the electron in that area. All right, so what it comes up with is, when he did it for a hydrogen, he came up with wave functions for that electron, and then taking the square of that function gives us this idea of electron density. All right, and so these electron densities, as they moved from hydrogen to helium to lithium, etc., 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 we move on to having more and more bizarre shapes that kind of pop up as we square these wave functions. Okay. All right, so just keep that in the back of your mind right now. We're going to jump, and we're going to remember those quantum numbers are those values that allow us to predict where electrons are going to be, right? Okay, so we're going to talk about our quantum numbers. All right, these quantum numbers allow us to predict the orbitals, or these areas of high electron densities. All right, so each orbital, or each set of 3 quantum numbers, allows us to predict that distribution of electrons. All right, so the first quantum number is the quantum number n. All right, these work very similarly to Bohr's model. Remember, in Bohr's model, we had n equals 1, then 2, then 3, then 4, 5, and as we went up, they got closer and closer together. Remember, so n equals 1 and n equals 2 is a big jump like this, and then n equals 2 to n equals 3 was a smaller jump, then 4, then 5, then 6, and it got closer and closer as you go up. All right, so that was the quantum number n. So it's just simply the energy level. N equals 1 is the bottom energy level, n equals 2 is the next one. They always have to be integers. Okay, so that's 1, 2, 3. You can't ever have an n equals 1.5. That doesn't work. That doesn't follow the quantum model that has been accepted as true. All right, or is currently accepted as true. All right, so and they always have to be bigger than 1. So you can't have a 0 energy level or a -1 energy level, etc. So integers greater than or equal to 1. All right. The next quantum number is quantum number L. L defines the shape of the orbital. Okay. Now you can start for L. You can start at 0, and you can go up from there. Okay. So essentially, what we have is just 4 for now until we discover more elements, and it depends on how high it goes. We could possibly have different shapes, etc. So we're just kind of on the edge of our seats to see what happens. But anyway, so we've got our L integers ranging from 0 to n minus 1. So within your energy level, so if you're at energy level 2, okay, then that means you can have you can have an L number of 0 or 1, because it can only go as high as n minus 1. So if you're at n equals 1, then you can only have an L of 0. Okay, and then if you're at n of 4, then you can have 0, 1, 2, or 3, right? Because you can go up to n minus 1, and since n is 4, and 4 minus 1 is 3. All right, so depending on what your L is, you get these different shapes, okay? And for the most part, we don't ever really use these when we're talking about things. We use these letters, okay? So when our L is 0, the shape of our orbital is described as an S orbital. When we have an L of 1, the shape of our orbital is described as P, L of 2 is described as a D, and L of 3 is equal to an F, all right? Finally, last one here is the magnetic quantum number, and this describes the 3-dimensional orientation. Okay, so remember, there's 3 axes, right? All right, 3 axes, and so we kind of we can be like along the x-axis, in and out of the page, y-axis, horizontal, or z-axis. So we can have these different orientations in space, and the higher we go, the more complicated they get. All right. So anyway, so our values for the magnetic quantum number, notice how it's m sub L, and that L is the L quantum number that we just talked about in the previous slide. So our m sub L quantum numbers can range from -L to +L. Okay, so any integer from there. Remember, so integers are whole numbers. So if we have an L of 2, then that means we can have 5 quantum numbers. We can have a -2, a -1, a 0, a 1, and a 2, because our L is 2. Okay, so anyway, so therefore on any given energy level, we can have up to one s orbital, because remember an s was a 0. Remember, s is 0 from right here. Okay, so s is 0 from right here. So as we go up, alright, so at an s level, we can only have one s orbital, because it's a 0, so we can only go from 0 to 0. Okay, but once we go to p, remember p is a 1 orbital, so we can have a -1, we can have a -1, we can have a 0, and a +1. Okay, and then 5 d orbitals, 7 f orbitals, and so on and so forth. Alright, so here's a breakdown of the table of everything we talked about so far. So our n values are here. Okay, so when we're at n equals 1, remember our L value can only go to n minus 1. So our only possible L value is 0. So that means we only have one subshell. Okay, so this is 1s because the quantum number is 1, and the s means our L was 0. So that's 1s. Okay, so remember our m sub L can only be between negative L and positive L. Well, a negative L, a -0, and +0 are the same number. Okay, so we can only have an m sub L of 0, which means we can only have one subshell. Okay, so there's our one subshell. So notice that, okay, when we have one electron, like, life's pretty easy. As soon as we get to more energy levels, life gets much more complicated. So here's n equals 2. All right, well, at n equals 2, we can have 2 values of L, remember, because L is defined as 0 to n minus 1. Well, if our n is 2, then that means we can have 0 for L, or we could have 1 for L, so 0 or 1. Okay, so the 2's mean we're on the second energy level. Alright, the S means, this S is designating the fact that it's a 0, and this P designates that our L is a 1. Okay, and then for our m sub L, well, at an s orbital, we only have the one m sub L, but once we get to P, we're going to have 3 different boxes, or 3 different orientations. Okay, 1, 0, and -1. So now we've got 3 subshells from the p orbital here, and 1 subshell from the s. Okay, 3 and 1, so we've got 4 total here. All right, and then we can continue move forward all the way through these. Okay, so anyway, so here's the general shapes. All right, so s orbitals are generally spherical shaped, and this makes life pretty easy. Okay, since there's no orientation in space, remember m sub L tells us there's orientation, and m sub L can only be between positive and negative L, and since L is 0, we only have one value, so there's only one orientation in space. So our s orbitals are spheres. Okay, and so the radius of the sphere changes with the value n. The higher the n, the bigger the radius. Okay, so look at this real quick. So this is pretty interesting. So here we've got a 1s orbital. These are our probability diagrams here. Okay, so we've got the density is really, really high right here. Notice how we don't get a lot right around the nucleus, and that makes sense. Okay, and then we get our maximum, and it says the maximum is around 0.5 angstroms. All right, so that's the most probable place to find our electron. Okay, so that's our 1s, and then as we get out farther, we get less and less of a chance of finding our electrons. All right, it's kind of interesting. The fact is that we do reach a minimum point, but we never quite reach 0, so there's always a minute chance that your electron could be like in Africa, okay, or something crazy, or on the moon. All right, anyway. So then as we go to like the 2s orbital, notice how there's a small chance for a small probability for our electrons to be between here within the 1s orbital area, but the most of them are going to be in the 2s orbital. Okay, so and remember, this isn't meaning that they're everywhere in here. These are just the likely places to find it based on the wave equations. Remember those? All right. So anyway, all right, so there's those guys. And then for 3s, notice that we get 3 humps, right? Now notice that we get nodes in here. So we've got between 1s and 2s, there's a node here, meaning there's a space in between there where there's no chance of finding the electrons. So here it is drawn out as like an actual piece of like a pie, or well, a sphere, right? So the white places are the places where it's not likely to find it. So this is the node in between these guys here where we're not likely to find that electron. All right, when we get 3s, we have 2 nodes. We got a node here, and we've got a node here. Okay, and they've kind of correlated these to our graphs for us as well. All right, so as we go up in n values, our electron density is more and more spread out. Okay, but it always maintains this spherical shape because it doesn't have an orientation. If it suddenly had some sort of shape, then we could start defining orientations, and then quantum mechanics falls drastically apart. All right, the next value for L is p orbitals. Okay, all right, so if your L is 1, then you have a p orbital. Now remember, p orbitals have 2 lobes and they have a node in between them. Okay, all right, and so we can have, and remember, our m sub L is always greater than or equal to the negative L and positive L, right? So if our L is 1, then that means our m sub L can be equal to -1, 0, or 1. Okay, so that tells us there's 3 orientations. All right. So here's our 3 orientations for the p orbital. We can have them sitting directly on top of the p-axis, or z-axis, sorry, the x-axis, or the y-axis. Okay, and it kind of bothers me that they changed up how they were graphing these. So now the x-axis is kind of going at an angle into the page, and so is the y. Instead of the y-axis kind of being, before they had it straight horizontal and more of the classical way to draw these, but whatever. I guess we won't pick on them too bad. Then we have d orbital. Remember, so d orbital has an L value of 2. This means that there are 5 orbitals, okay, for the d orbital. Now 4 of these are pretty easy, and they just sit right on these planes, and they're defined by these planes. So the first d orbital sits on the yz plane, meaning that it kind of fits right here on this flat spot, coming in and out of the page right here. And then we have the xz plane, so it's kind of like this plane that's x and z. And then we have the yx plane right here, or the xy plane. All right, then life gets more exciting. So those are the first 3. Then life gets more exciting. Moving on from there, we get the x squared minus y squared. Okay, so it kind of has this orientation. So notice it's very, very similar to this orientation, but instead of the lobes being equidistant from the middle, they're aligned with the lines here. So that's the big distinction there. And then finally, the z squared plane kind of looks like a donut with a p orbital through the middle. All right? Okay. And then the f orbitals are very complicated. We don't really show them. I've got models at school to show you, so we'll look at these a little bit closely. Okay, but there's 7 equivalent orbitals, all right, and because their L is equal to 3. Pretty exciting stuff, okay? So here we go. So let's look at the energy levels of these orbitals. So remember, with the Bohr model, it predicted the hydrogen model really, really well. Okay, so we start at n equals 1, 2, 3, etc. So when we start at n equals 1, we can move up to n equals 2. Now for a hydrogen atom, it only has 1 electron. Okay, so all of the n values have equal energy, which is really weird and not like any of the other elements, which is why the Bohr model worked for hydrogen and nothing else. So within that energy level, all of these had equal energy. So n equals 2, this guy all has equal energy. N equals 3, all of these have equal energy. So specifically for hydrogen, it's got what are called degenerate orbitals. Most other elements don't have degenerate orbitals. It's a little bit more complicated. All right. So when you have a hydrogen atom and your electrons go up and down, up and down, up and down, they're jumping just to the energy levels, and they could be in an s, p, d, or f orbital. Doesn't matter, okay, because they all have equal energy. However, for all the other elements that have more than 1 electron, okay, their energy levels become more striated, if you will. There'll be more levels. Okay, so they kind of follow this order. Okay, so the S's are always less in energy than the P's, and which are less than the D's, which are less than the F's. Okay, now look, so it goes from 1S, and then the next one is 2S, then 2P, then 3S, then 3P, and you would think to yourself, oh, 3D would be next, but not quite. No, life's not that simple. The next energy level is 4S, and then you get 3D, and then 4P, okay, etc., etc. So this is an important distinction to make, especially in the next video when we start talking about electron configurations. All right, so we've got the spin quantum numbers. So this is the last quantum number, and this guy's I think it's the second easiest one. N is pretty easy because it's just the energy level 1 through infinity. All right, the spin quantum number tells us which way the electron's spinning. It can either be spinning clockwise or counterclockwise. All right. And so we call it m sub s, okay? And it can either have that our electrons can either have a spin of +1/2 or -1/2, all right? So that they can be either spinning positively or counterclockwise or clockwise. And so we get this idea, and this is the last slide for this video, okay, of this Pauli exclusion principle. And this is the fact that no two electrons in the same atom can have the same set of 4 quantum numbers. So if you have an atom and you find the quantum numbers for one electron, no other electron can have the same 4 quantum numbers. So they can't have the same n, l, m sub l, or m sub s. Okay, so that means that no two electrons in that atom have the exact same energy. Okay, and so this allows us to come up with what are called electron configurations, and that's what we'll spend the rest of the chapter talking about. All right, if you have any questions, let me know. I'll see you in class, do some practice problems, and I'll catch you on your flip side.